Hello everyone and welcome to a new discussion under this groundwater engineering course, and today and on two more occasions we would be talking about Darcy law. And as you learn or might be knowing that this is the very important law in groundwater hydrology or groundwater engineering, which governs the basically the flow of water and in subsurface conditions, and what are the influencing factors, and how we can estimate various parameters which are related with groundwater engineering, that we will be discussing. So, there will be 3 lectures. So, this is the first part of Darcy law. As you know that this is an empirical law and is an equation, and that is basically will describe the flow of a fluid through porous medium. So, these are the important words, that if a medium is not porous, means that rocks does not have a space or fractures or pore spaces and connected spaces, then in true sense the Darcy law cannot be applied. So, it is a basically flow of a fluid through the porous medium, and in our case the fluid is of course the water. So, this law was formulated or given by a great hydrologist whose name is Henry Darcy, and which is based on a result of series of experiments, and that is why this empirical law came in existence, and that was in the year 1855 and 1856. So, way back it was developed, and since then world over people are following this law to see the flow of water in aquifer conditions. So, on this flow of water through beds of sands forming the basis of groundwater hydrology. So, this is very important law in groundwater hydrology or engineering. Darcy law comes from the Henry Darcy's in 19th century, who was a French water engineer, and that gave. So, let us come to what is basically, after seeing the historical part and who developed. Now, let us focus on what exactly Darcy law. So, on the right side which you are seeing a pipe or a tube which is filled with the sand or porous material, and there are 2 places where we can measure the level of water. So, it is denoted with X and on one top part and then Y part, and there is also slope is there, and so this the difference between the water level in X tube and the water level in Y tube, that is what is our HL head level, or the difference between 2 heads, and the L here is denoted as the length of the tube in this case, or in case of aquifers it can be the length of the aquifer. And secondly, the cross-sectional area, which is also shown with the red ellipse, but if you see a front view, it would be definitely circle in this example. So, there is a water input from this side, and this is the water outlet. So, basically the Q can be also measured here. So, what Darcy law states, Darcy law says that the flow rate Q that will be coming out of outlet is proportional to cross-sectional area. So, this is directly proportional to cross-sectional area. So, that means that if a cross-sectional area is large or more discharge would be there, and the head loss HL. Now, also comes that head loss. So, what is the head difference between these two? So, this HL is head loss and inversely proportional to length. So, if length is more, the Q, it is going to affect the Q. So, let me go through again, that the flow rate Q is proportional to the cross sectional area A, which is shown here in the figure, and the head loss HL, which is also shown in the right figure, and inversely proportional to the length. So, that is, it is proportional to A, that is cross sectional area A, and to hydraulic gradient. Hydraulic gradient is considered as HL, that is head loss divided by L. So, by which now we can go for further explanation of Darcy law or further understanding, which we will try, that the head loss HL is the difference between two monometers as x and y, which we have just discussed, and which are a distance L, which is apart from the measured along the direction of flow. So, in groundwater conditions, it would be the length of the aquifer, and this cross sectional area would be like what is the cross sectional area of an aquifer which is coming inside a well. So, that can become, and head loss if we want to measure, then at least we should have water level at two places. Then we can apply Darcy law and can estimate the Q, that is discharge coming from a well. So, if we double the flow rate Q, suppose if we want to increase more output or we want to have more water, then we find that the HL doubles also. That means this head loss would also be doubled. So, this will increase, the level in these two monometers will change, and if half Q, if we go for less discharge, then also it becomes half. So, in that way it is proportional. Now, in general we find that the flow rate, and that is Q, is directly proportional to the head loss, and that is, so we can write like this, the Q, that is discharge equivalent proportional to HL. So, there is a direct relationship. Now, we will further develop further develop our understanding to go to exactly what Darcy law is, that if we vary the length of our sand filled pipe, or in case of our groundwater hydrology aquifer, but keep the same head loss between the ends, that is between x and y, the L length, then we find that the L increases. When L increases, Q decreases, and vice versa also. So, if we double the L, we find the Q is half. So, if the length of the aquifer increases, say it goes double, your discharge is going to be less. Anyway, so in general now we have seen a different relationship, that the Q is directly proportional to 1, and that is 1 upon L, and whereas we can write Q proportional to HL. So, if we combine these two equations, then we end up with Q is proportional to HL by small l, divided by small l, and this is HL, as we have just discussed, that this is the hydraulic gradient, the difference between x monometer to y monometer. So, the rate at which water flows through sand in this example or in this setup, lab setup, is proportional to the hydraulic gradient. This is very important statement, that the rate at which water flows through sand is proportional to hydraulic gradient. So, if you make more discharge, then the HL is going to increase. So, if we put another identical cylinder say in the experimental setup beside the first one and filled with the identical sand, and with flow occurring in the same way, we would have in effect twice the flowing occurring through twice the cross sectional area. So, it will basically double. So, therefore, it can be assumed that Q is proportional to A, that we have also discussed. So, in summary, what we can say, that Q is proportional to A, cross sectional area A, and hydraulic gradient, which is HL upon L. So, we can now write that Q is K, and here the K is basically constant, and which is also the property of soil, water, soil, rock or aquifer. And so, the K A H L upon L, that means K constant, A cross sectional area A, H L and L is the hydraulic gradient. So, Q is is equal to all these three parameters. So, since we can measure at any time, even in through pump test, we can measure the Q, and we can also measure the A and HL, and hence we can calculate the value of K. So, we can determine this constant value. So, if we replace all these values which we have determined in the equation, we will get the value of K. So, it replaces sand with, suppose we do the further experiment as done by the Darcy, that sand with finer sand and then repeat the same experiment, we shall be getting relatively smaller value of K. Why? Very simple, because a coarse sand will allow more discharge. So, the material, that is why K is dependent on the material which is a aquifer is made of, or material filled in this experiment in the tube. So, K is proportional to that material. So, if we replace it as coarser, then what currently it is in the sand, or let's say with pebble or cobbles, then the value K would be larger. So, then we can conclude that therefore, the K is permeability or hydraulic conductivity of the sand at this stage. So, K we can denote here as permeability or hydraulic conductivity of the sand, or in real situation of the aquifer. So, what we can further go through that finer sand, coarse sand or sand. So, in this case coarser sand is more permeable than the fine one, because the spaces between coarse grains are correspondingly larger and allow on easier passage for water. Now, let us link with the real situation like in aquifer conditions. So, if we are having a shale, then we are having very fine materials, and we may have good porosity, but we may not have good permeability. That means the value of K may not be there, and therefore, the Q is going to be less. Contrary to this, if we are having a coarse sandstone, and then the permeability is going to be high, the pore spaces and connectivity is going to be large, and therefore, we can have more Q. So, a coarser sand will have high specific yield, and however, it will have low specific retention. Now, so we have used now two new terms here, specific yield and specific retention, which we will have a special discussion or detailed discussion on these little later. So, further we can repeat our experiment with sand filled cylinder, keeping all other things same, except instead of water, if we use the material which is having high viscosity like a syrup, we will find the flow rate is much less than water. So, the fluid which is flowing through the system also plays the role. Even the temperature will affect. So, even the pollutants will affect in case of groundwater, and in case of groundwater the temperature will also affect. So, that means the viscosity is now playing some role here. So, in such case the value of K would be smaller. If viscosity increases, the hydraulic conductivity is going to be less. So, hence the hydraulic conductivity K depends not only on the porous medium, but the fluid itself, and which is filling the pores and passing through them. So, this is another important factor which controls our discharge. So, in case of groundwater engineering, everything have to be kept in mind, and therefore, we get the correct estimations of Q. Otherwise, if we do not consider all these factors, then that will not be good estimates of the Q. So, this property of fluid which we are discussing, if it become more viscous, it affects the K. If it is having high temperature, may not have even the water, then it will affect again in a different way. So, that affects the hydraulic conductivity, the kinematic viscosity, and which we can denote as V or nu symbol in the Greek that we use. So, as the kinematic viscosity of a fluid in a porous medium increases, the hydraulic conductivity decreases. So, basically viscosity, if viscosity is high in case of syrup compared to water, then of course, the hydraulic conductivity is going to less, and if hydraulic conductivity is less or decreasing, then of course, the Q will also be decreasing. So, this kinematic viscosity of water decreases as its temperature increases. So, if the same fluid is there, but there is a temperature difference, then this viscosity factor will decrease, will reduce, and when temperature is going high. So, if you are having a like a very shallow aquifer conditions where the atmospheric temperature variations can affect the viscosity of water, therefore, it will also affect your K and output. So, now we come to this part about the summary, how we can summarize this, that Darcy law states that the flow rate Q, that is discharge, will be directly proportional to the cross sectional area A, and through which flow is occurring, and directly proportional to the hydraulic gradient. In that way, if we read this one carefully, it is a very simple law, that it says that the flow rate Q will be directly proportional to cross sectional area and also directly proportional to hydraulic gradient. But in nature, things are not like as we have seen in the experimental setup. The things are varying, and many times it becomes difficult even to find out even HL in real ground conditions or in groundwater conditions. So, therefore, we have to be little careful while applying Darcy law in case of field related estimations. So, now we come to end of this I would say a brief discussion. Since this is part 1, we will have more discussion on part 2 and 3, that the Darcy law, now considering equation 1 which we have already said, that is the Q equal to K A, hydraulic conductivity K, A is cross sectional area, HL upon L is the hydraulic gradient, then it can be stated that Darcy law, that a fluid will flow through a porous medium at the rate which is proportional to the product of cross sectional area A, through which flow can occur, the hydraulic gradient and hydraulic conductivity. The viscosity part will also come, or temperature variations and other things will also be incorporated in this, because they will affect my hydraulic conductivity. So, just remember that Darcy law is Q equal to K A H L upon L. So, this brings to the end of this discussion. Thank you very much. We will discuss further in details in part 2 and part 3 of Darcy law. Thank you.